I'm going to end with just talking about a couple of planets in our solar system. So here is planet Earth, as hopefully many of you are familiar with. That's our own planet. And this is our sister planet, Venus, as taken by the Pioneer spacecraft. And both planets are very similar in size and similar in mass. Venus is about 30% closer to the sun, and it receives more sunlight, obviously. But the one critical difference between Earth and Venus is that Venus has a much, much thicker atmosphere. And this thick CO2, mostly CO2 atmosphere, results in a runaway greenhouse effect on the planet so that the surface temperature is hot enough to melt lead. And in terms of the size of the atmosphere or the mass of the atmosphere compared to the entire planet, the Earth's atmosphere is about 1 million times less massive than the mass of the Earth. But Venus's atmosphere is about 100 times larger than the Earth's atmosphere, so that when you compare the mass of Venus's atmosphere, it's only about 1/10,000th the size compared to the mass of Venus. So one question that planetary scientists who study the evolution of the solar system have is, how did these two planets end up to be so different as far as their atmospheres? Why did Venus end up having so much atmosphere, and why did Earth end up having so little atmosphere? And one suggestion, and right now people don't really know, but one suggestion that scientists have offered is that perhaps Earth might have had more of an atmosphere, but it lost it early in the solar system because of impacts. And so early in the solar system, there was still a lot of debris in the solar system, and a lot of this debris was accreting onto all the planets. And the Earth, along with all the other planets, were constantly bombarded by small and large objects. And so, and people have argued and modeled and wondered, whether how much of a factor impacts might have had in removing the Earth's atmosphere. And so that was the goal of this particular paper, atmospheric mass loss during planet formation, and the importance of planetesimal impacts, led by a researcher at MIT, Schlichting. And just to clarify, this picture did not appear in their paper. But what they worked on was they came up with a model that had different impactor scales. And so the largest impact in their model was something on the order of 1,000 kilometers or larger. And in this case, in the physics that they worked out in this model, when you have something that big, not only are you colliding with the planet and then creating ejecta, meaning an explosion that throws out huge amounts of the crust as well as the oceans and the atmosphere in this region. But what they show in their paper is that there's also a shock wave that propagates through the planet because of this collision and this impact. And the shock wave spreads all the way over to the other side of the planet, and it's massive enough of a shock front that it can actually eject the atmosphere clear on the other side. So this is for a super enormous impact. And they also looked at smaller impacts for a size range between, let's say, about 25 kilometers and up to about 1,000 kilometers. You can have an impact where it basically wipes out all the atmosphere in a tangent plane. So if you imagine a straight sheet of paper that just touches the impact point, an impact between 25 to 1,000 kilometers can basically remove all of the atmosphere from here on up. That's how powerful those impacts are. And then for impactors that are smaller than about 25 kilometers, you remove successively smaller and smaller amounts of the atmosphere. So they basically went and modeled all this in their work, and what they showed is, this is a kind of a complicated plot, but this is the number of impactors that's necessary to eject the entire Earth's atmosphere. And so what we have on the bottom is the size of the impactor. So here's 1 kilometer, 10 kilometers, 100 kilometers, and 1,000 kilometers. And this is n, the number of impactors. And so here's 100, 10,000, a million, 100 million, 10 billion. And for anything smaller than about 1 kilometer, you basically need effectively an infinite number of impactors to remove the Earth's atmosphere, because things just burn up in the Earth's atmosphere when they're too small, so they really can't eject any of the gas from our atmosphere. But you can see that for impactors between 1 and about 25 kilometers, you need on the order of about 100,000 to a million objects. And then it goes down to a few thousand. And then for these super giant impact scenarios, you get down into the tens and the hundreds. Now the critical graph is here, where here, instead of looking at number, we look at the amount of impactor mass. And so if you added up all of the planetesimals that are falling towards the Earth, how much mass would it take? And again, the impactors that are smaller than a kilometer, you basically need an infinite number of them because they just don't do anything to our atmosphere. And when you have the super large impactors over 1,000 kilometers, here's 1,000 kilometers again, you effectively need about roughly about this m with the circle and the cross that's supposed to represent the mass of the Earth. So what this means is that you roughly need about the mass of the Earth to collide with the Earth to eject all the atmosphere. But the most efficient way to do it is actually within this regime between the 1 and 25 kilometer impactors, where you only need a very small amount of mass, so on the order of a millionth or 100,000th of the mass of the Earth. And early in the solar system, we find that there are far more small impactors or small pieces of debris flying around than large impactors. So it's entirely reasonable, based on this model, to suggest that the Earth probably did undergo an episode where it lost all of its atmosphere due to these small impactors. And so you only needed a small amount of mass to eject the entire atmosphere of the Earth. And the most efficient impactors are actually only about a couple kilometers across. So this is a painting by Don Davis, I think supposed to showing the Yucatan impact. So impactors only a fraction of the size of this one. And based on some other research, people have actually argued that the Earth might have not only lost its atmosphere once, but maybe twice early in its history. And this research helps to sort of corroborate some of those tentative results. So that's pretty exciting.